positive. What do you think he was trying to say?
It's ever increasing.
It's increasing, right? Over time, his love is increasing for her. That's very romantic, isn't it? Isn't that romantic? Okay, but I quickly pointed out to him that there's trouble with that if his wife knows enough about math. And that is, look at this. What if you have a function that has a horizontal asymptote like this and does something like, maybe even like almost like the square root function. It goes like this. Okay, that function is increasing always. As you go to the right, it goes up. But it's asymptotically approaching this dotted line. It will never get to it and it won't ever pass it, right? So the first derivative of this function is always positive. However, there exists some capital M that is bigger than the function all the time, right? So if I just go up here, I say, look, you may love her, but you don't love her that much. You missed all the other stuff. Okay, so you may, like you walk out for 30 seconds, you come back and we're talking about, okay, so you may love her, right? But you don't love her that much, right? So I said he needs to tweak it a little bit. So what other condition could he add to that to get the point that he was trying to get across?
With no restrictions.
Well, yeah, he could say, it's not bounded or something like that. But something about the second derivative. What if it's concave up? See, the only way you can have an asymptote like this is if you're concave down. So if I just said, look, add the condition that the second derivative is also positive, and then you are unbounded love. Then you're unbounded love, right? Because you got to go concave up. Now that's romantic, right? The good old days. We'll have to explain later.
Watch the video.
Yeah, watch the video. All right, here we go. Here's what we want to do with this. We want to know where it's increasing, where it's decreasing, local max, local min, concave up, concave down, inflection points. All of it. All right? So if we want to know all that, we want to know where the function's going up. We want to know where the function's going down. We want to know max. We want to know min. We want to know concave up. We want to know concave down. And we want to know inflection points, IP for inflection points. Then we're going to need to be working with both the first and second derivatives, right? So sometimes what I like to do with these problems is just go ahead and get that part out of the way to start. Let's just figure out what the first derivative is, clean it up, look at the second derivative, clean it up, and then we'll proceed, yeah? Okay, so let's take a look at these derivatives. First derivative. Thing about that guy, he was a jerk, man. He would cheat on his girlfriend and stuff. So I mean, he really should have been negative derivative on that. Really, he was bad guy. Bad guy. Okay, so yeah, I'm on. All right, here we go. First derivative. First derivative. What is the derivative of the square root of something? 1 over 2 square roots of that something times the derivative, what's inside? 2x. Now we are done with this, right? We have taken derivative of this, but we still need minus derivative of that, so minus 1. And let's just clean up. Okay, 2 here gone. I'll just slide that x on top. X over square root of x squared plus 1 minus, x squared plus 1 minus 1. There it is. There's our first derivative. We'll have to set it to 0 in a little while, all right? which we'll do. But for now, let's just leave it. Let's go ahead and try and take the second derivative now. Second derivative isn't going to be very nice. Because I don't think there's any way to get around quotient rule there. I mean, you could like bring it up as something to the negative 1/2 and use product rule, but let's just go with quotient. Derivative of the top is 1 times the bottom. Okay, minus derivative of the bottom, which is another one of these 1/2 root things, right? So we have 1/2 square roots of x squared plus 1 times 2x. It's like we did that already, didn't we? So we have derivative of the top, which is 1, times the bottom, minus derivative of the bottom, here it is, times the top, right? We still need times x, and then all of that over x squared plus 1. So we're actually kind of happy that that square root was there, because when we square it, the square root goes away. That doesn't look that fun, but, you know, at least those 2's cancel. So here we go. We've got root x squared plus 1, and then we have minus x squared. Let me put a little line between this so you don't confuse that. X squared over square root of x squared plus 1, and then all of that over x squared plus 1. So all I did there was took the x's, multiplied them together, put them on top there, cancel those 2's. There's our second derivative. We'll have to set that to 0, but, you know. All right, we got it? Okay, let's start working on the first one. Let's do our increase, decrease, local max, local min. Yeah, we're gonna come back and do some algebra on this. Oh, hey, we never talked about domain. Oof. We never talked about domain. Are there any domain restrictions? We just got to make sure that this is never a negative number, and it can't ever be. Because when you square anything, you're going to get positive. The worst that could happen is you get 0, right? 0 squared. But then when you add 1 to it, you're still positive. So no issues. Had this been a minus sign, different story. But it's a plus. So no domain issues. We're good. All real numbers. The graph should exist everywhere. All right, first derivative. We're going to try and find the critical numbers. Let's figure out where the first derivative is 0. So I'm going to take x over square root of x squared plus 1 minus 1 and set it to 0. I should get a common denominator, no? All right, so the top is going to be x minus what? Square root of x squared plus 1, right? Because you have to do square root of x squared plus 1 on the top and the bottom, right here. And then put them together, that's all over square root of x squared plus 1, and then set that to 0. That can only be 0 if the top is 0, right? So we set the top of that equal to 0. And that equation is called a radical equation, and that's something that you hopefully learned in college algebra, how to do those. What are the steps to solve a radical equation or a square root equation? No? Isolate the root. Isolate the root. Get the root by itself first. Get it by itself on one side of the equation. So I'm just, since this is a minus, I'm going to move the root to the other side. And what's the whole purpose of doing that? So you can square both sides. Now, as soon as we square both sides, there's a little alarm that should go off in your head that says you're going to have to check your answers. All right? When you square both sides, that happens. That has to do with what we were talking about earlier. Yeah. Remember about the 1-to-1? Okay, but that's, yeah. All right, so square both sides. Square the left becomes x squared. Square the right becomes x squared plus 1. What? 0, 1. Did we mess up? No, we didn't mess up. What is this saying to us? What is this saying to us?
There's no place when first derivative equals 0.
Yeah, so we were asking, when is the first derivative 0? And the answer is never. Okay? Never. It's never 0. What does that mean, though? Like, if it's never 0, then it's either always positive or it's either always negative. Right? So we don't know what it is yet. Okay? We don't know, but we can tell you right now it's never 0. Okay, so good. Now the next thing we need to look at is, when is the second derivative, first derivative, not exist? And so when we look at this, here's our first derivative kind of cleaned up right here, right? The only time we would not exist is if this in here was negative or if this down here was 0, which again, you cannot have happen. Like, it's just not going to happen. There's nothing you can plug in here to make this 0. So no issues, right? This means we have no critical numbers. There's no critical numbers. So what do you do on the number line? You just test any point you want. And whatever it is what the whole function's doing. Okay? So I'm going to go to a number line now. And I'm going to say, all right, here we go. Put my critical numbers. Don't have any. So I get to pick any point I want. Let's do 0. 0 is always fun to plug in, right? So plug 0 into the derivative, which I've erased. But what was that first derivative? I think it was this over x squared plus 1, right? What's that?
Square root over x squared plus 1. Bottom is square root.
Yeah.
This is square root. Oh, this. Oh, yeah.
That's the second.
That's the second one.
Yeah. So it's x over x squared plus
Oh.
1 minus 1.
No, you're right.
Oh, the top is right?
Yeah.
Okay. So that's our first derivative.
Yeah.
Okay. So let's plug 0 in, and what do we get? Negative 1 over 1. So you get negative. What does that mean? If our first derivative is negative when we plug in this test point, that means our original function is going down all the time. It's always decreasing. So we did into the first derivative, we plugged in 0, and that turned out to be a negative number. So if we're saying that the function is always going down, does that mean it's just going to keep going down forever? The love function. The love function. Think about it. If I say that my love for you is decreasing always, does that mean it goes forever? No, it could asymptotically still approach something. So we still don't know if this graph just keeps going down or if it goes down and kind of flattens out, if that makes sense, right? We need to know a little bit about the second derivative.
But there's no max or min, though.
What's that?
There's no max or min.
No max or min what?
Right? How am I supposed to find the max min?
Yeah, there's not going to be a max or min yet. Yeah. I'm just trying to make sure everyone understands that just because a function goes up forever or down forever doesn't mean that you've got this like graph that goes up or down forever. You can still have asymptotes that they flatten out. All right? Okay, now let's kind of summarize now from this first derivative. Where is f increasing? Where is f decreasing? And what are any max or mins? So let's do the decreasing first, because the decreasing we know, right? Where is it decreasing? Everywhere, right? So negative infinity to infinity. All right, so what is our answer for increasing? Never, right? How do we say never using the notation, interval notation? So this is what we use for interval notation to mean everything, right? What is the notation we mean for nothing?
Empty print?
That is the empty set. So I don't know, I don't think it's a student in here, but I have a student, I think in my Cal 2 class, that is consistently using that for the number 0. And That's not wrong because in the military they do that. In the military they strike through their zeros so you don't confuse them with O's. But in mathematics, a 0 with a strike through it is the empty set. And that is not the same as the number 0. So think of it this way. If I have a basket, okay, and I throw some numbers in there, I can throw the numbers 1 in there and 5 in there. I could take the number 0 and I could throw it in there, right? And then that basket would have the number 0 sitting in there. If I have a basket that has nothing in it, that's the empty set. It's the set of nothing. 0 is a number. It is not a set. So they're completely different animals, if that makes sense, right? It's like this is a cat, and that's an orange. I mean, they're just completely different things. Sets and numbers are different things. So moving along in your life, if you're going to do more math, even if you're former military or current military, I would stop using that for 0. Start using 0 for 0, all right? And use that only for the empty set. Okay, do we have a max or min? No, so none. No max or min because we don't go up and down or down and up. All right, so the first derivative actually worked out not that bad, right? Now we got to go handle this second derivative, which I've left on the board here. We need to go do that, set that equal to 0, figure out where it's undefined. All right, so second derivative, let's clean up the second derivative. It's not bad? Okay, good. So my second derivative, let me try and start putting things together. When I get a common denominator, I'm actually going to do the top first. So I'm going to go this over 1 and just get a common denominator between these two, which means I need a root x squared plus 1 here and then a root x squared plus 1 there. And that's actually really good because this root and this root go together and the roots go away. So you just get x squared plus 1 and then minus x squared. I'll go ahead and write that down. X squared plus 1 then minus x squared. That's all over the common denominator we got when we put these two together, which is the square root of x squared plus 1. But that's all still sitting on top of x squared plus 1. That's a complex fraction. Yeah, we can do some stuff to this, but really you can also use the same principle we used a while ago. A fraction can only be 0 if what? A fraction can only be 0 if what? The top is 0. So all I have to do is set that to 0, right? But that's a fraction. So I can just set the top of that to 0, which means the only way this can be 0 is if what? The top is 0, right? What is the top? Yeah, this is all 1. So basically this only happens if 1 equals 0, which never happens. Are y'all following me or not? Did I go too fast? It's okay. Okay, so this fraction, this over this, can only be 0 if the top is 0, right? So imagine taking that and setting it equal to 0. Now, since that's a fraction, that can only be 0 when the top is 0. So ignore that and just look at that. But that's x squared plus 1 minus x squared. So the x squareds are gone. And that's just 1, right? So what we're saying is for the derivative, second derivative to be 0, we need 1 to be equal to 0, which ain't happening, right? So 1's not 0, which means we have no critical numbers from this. We also have check is the second derivative ever undefined. Well, if you go back, we have the same issues we had earlier, right? Do you have division by 0 ever? No. Do you have any negatives under roots? No problems. So what are we going to do? Number line. Pick anything we want, like 0, and plug it into the second derivative, which I'm just going to go back to this one. Well, no, I'm going to go to the one that we cleaned up, because the cleaned up one looked like this. 1 over square root of x squared plus 1 over x squared plus 1. I think you can just look at that right now and tell, hopefully you can, that no matter what you plug in, you're getting positive numbers out of everything, right? That's our second derivative cleaned. So it's always positive, which means we are always concave up, smiley, happy, positive people. Okay? All right, so let's conclude now. We have Our original function is concave up where? Everywhere, negative infinity to infinity. And our original function is concave down at 0. Military 0. Empty set, right? It's never concave down. How about inflection points? None. All right, so this problem looked bad. The derivatives were a little messy, but other than that, I mean, it's not very interesting what's happening. So I'm going to graph it. Square root of x squared plus 1, and then minus x. There it is. Pretty boring. Pretty boring. Always decreasing, right? Always decreasing. But, see, we have an asymptote. Looks like it has an asymptote. So we have this, and it's always concave up, right? This is smile, still smiling the whole way. It's a very flat-looking smile, but it is smile. All right? Oops. Oops. Okay, we need to talk about something called the second derivative test. And then we'll be done with this section. So the second derivative test. Right now, as it stands, if we want to find the local max or the local minimum of a function, what do we have to do? Local max or min, what are we going to have to do? Take the derivative, set it to 0, critical numbers, number line, test points, look for up and down, down and up, right? Make sure those points are in the domain. That's what it would take, right? This second derivative test is a thing we can do that could possibly shorten your effort a little bit. And sometimes it's harder. So it's good to have it as a tool, but not always used. In fact, personally, I don't use the second derivative test very much at all. Like, it's nice to know it, but I don't like it. Okay? Here's what the test says. It's actually a pretty cool test. It says, let's say we are looking at a function, all right? Let's say that we go to some point on the curve, and we discover that at that point the derivative is 0. Okay? So we have a curve. All I know about this curve right now is that if I go to this particular point, the derivative is 0, which means we have a flat tangent line. Okay? Does that mean that I'm at a max or a min? No. Critical number means I might be at a max or min. We've seen curves that look like this, where that is definitely got a derivative of 0, but it's not a max or a min, right? So just knowing where the derivative is 0 isn't enough to say it's a local max or min. But what if I also tell you that not only is my derivative 0 here, my first derivative 0, what if I also tell you my second derivative is positive? Then that means we'd have to be concave up there. And that means your curve must be at a local minimum. Do y'all see that? If you have a flat tangent line and you have concave up, you're looking at a minimum. See on this one right here? We have a flat tangent line, don't we? What's the concavity here? What's the concavity on this side? Are we concave up or down here? Concave down. Over here we're concave up, right? So it's like frown, smile. This is saying if you go to the point and you have a flat tangent line and you're basically smile, smile on both sides, you've got to be at a minimum, right? Now, what about the other way? Right. Go to a point, derivative is 0, but now you're concave down there. Then you got to be looking at a local max. And that's what the second derivative test says. Here's the test. Suppose the second derivative is continuous near C. That means the second derivative exists. If the first derivative of the function is 0 at some point, C, and the second derivative is positive, so flat, concave up, you've got a minimum at that point. If you have flat, concave down, right, you're looking at a local max. Make sense? So I'll show you something. I don't want to get into too deep into an example of this, but I think it might be worth. Well, we'll do 2 examples. Take a look at this right here. It's a very basic function. I understand that. Okay. That function right there should have a local what? Local minimum, because it's a parabola that opens up, right? Let's run the second derivative test there. So first let's take the derivative. What's the derivative of this function? 2x minus 4. Okay, let's set that equal to 0. We set that to 0, what's our solution? 2. Okay, so we know that when we graph this at x equals 2, I don't know where I am, I don't care where I am, but at 2, I've got a flat tangent line, right? Now let's look at the second derivative. What's the second derivative of this function? It's just 2, right? And so what I'm supposed to do is I'm supposed to go to this value 2 and see what the second derivative is there. But it's always 2, isn't it? Which means it's always positive. And if it's always positive, that means it's concave up, right? So that means that we know that this thing is concave up. And that means that I have a local minimum at x equals 2. I know that. Make sense? So if the function is easy to differentiate, especially if the second derivative is nice, then it might be worth you doing this. Let's do another one. Let's do another example, because that one's a little too basic. I might regret this. It was in the book. It was in the book.
Can't blame you.
Let me see here. Just make sure this is what I saw. Oh, okay, sorry. Arctan. All right. Let's just talk local max and min right now. Okay, not all, where is it increasing, decreasing, where local max, local min, concave up, concave down. Let's not do all that. All right. Let's just see if we can just find local max and mins. Okay, so if I'm going to use the second derivative test, if I'm going to do it, I've got to take the derivative twice. Okay, so let's take the derivative twice. First derivative. I guess maybe I should back up. If you want to find local max and min using the table and the test points, you only need the first derivative for that, right? For local max min. If you're going to use the second derivative test, you don't need to draw the table, but you got to get a second derivative, right? Which might not be fun for you. Let's see if it's fun. Okay, what's the derivative of e to the arctangent of x? What's the derivative of e to anything? Itself, okay, times the derivative of arctangent of x, which is 1 over 1 plus x squared. Good. All right, now that is just e to the arctangent of x over 1 plus x squared. That sucks. No, it only sucks because that derivative is never 0. So we're not going to have a local maximum. This thing can never be 0. Why can this never be 0? Fraction can only be 0 when the top's 0, right? And e to any power, right, should never be 0. So, oh well. Second, we're not going to have a local maximum in here. That's what I'm getting at. Let's do second derivative just for fun. Okay, so derivative of top, right, which is that, right? The derivative of that is that. So e to the arctangent of x over 1 plus x squared, that's the derivative of top, times the bottom, right? Ooh, 1 plus x squared. Minus the derivative of the bottom, which is 2x times the top, all of this over bottom squared. That is your second derivative. Shall we run through that again? Derivative of the top is actually derivative of the original thing, which is itself, times the bottom minus the derivative of the bottom times the top all over the bottom squared. These cancel, which is nice. And even more than that, if these cancel, these two terms both have an e to the arctan x in them, right? So I can factor it out. So this actually turns out to be not too bad. E to the arctan of x factored out, I should get a 1 minus 2x. Then on the bottom, I have this 1 plus x squared squared. And now I'd have to set that equal to 0 if I was trying to. So I think on this problem, this appears in the book. This is the last problem in the section, and they want you to find where is this function increasing, decreasing, local max, local min, concave up, concave down, inflections. So you would need to do this and set them to 0 and stuff. Okay, I'm almost out of time. I wanted to talk about one thing. One of your classmates asked me a question the other day about what the derivative of the square root of not square root, the absolute value of something is. So I don't think I ever formally went through this. I think I informally did, but I'm gonna do it the simple way. There's some things that we've taken the derivative of, or I've just told you the derivative of this is this, and just take it on faith. Like arctangent, you just said it was 1 over 1 plus x squared, right? The derivative. I just told you all that's what it was, right? Like, I don't think I went through the proof of that. So I'm going to give you an example here, or a formula now for the derivative of the absolute value of something. So if f of x is equal to the absolute value of x, then the derivative of this is just, you can write it either way, absolute value of x over x, or if you want, you can flip it over and put x over the absolute value of x. I don't recall if that formula is in the formula sheets. I don't think it is, though. I mean, you can check. It would be under your differentiation rules. You have it there? Let me see. Let me see. I don't think it's here. Oh, no, it is. Formula, oh, no, that's not it. Yeah, I don't see it here. Okay. Bonus material. So I'll just show you real quick visually what the motivation is behind this answer. If you go and look at the absolute value function, the absolute value function looks like a V, like this. So if you're anywhere to the right of 0, then if I go to any point here and go up here, what's the slope of the tangent line going to be? What? Yeah, positive, but even more than that. There's something about this. This diagonal is like the perfect diagonal. So the slope of that's going to be 1, right? In fact, that's going to happen anywhere. Anywhere over here to the right, if I go and I look at the slope of the tangent line, those slopes are always going to be 1, right? So we know that the derivative over here should be 1. But then when we go on this side, what should the derivative be? It should be -1 because the slope is this way, right? So what we need is for the derivative to spit out 1 if you plug in a positive number, and to spit out -1 if you plug in a negative number. Do you agree? So what we do, let's just use one of these. I'll use this one, okay? So think about what this answer is going to be. If I plug in a positive number, that's going to be positive over the absolute value of any number is positive. So this is going to be positive number over the positive of itself, which will be 1, right? So if I plug in anything over here, I'm going to get 1 from that. But if I go on this side and I plug in, let's say, -2, the top here is going to be -2, and the bottom is going to be the absolute value of -2, which is 2. So that ratio is -1. So that'll spit out, as long as you're to the right, you're good, right? The only issue we have is at 0. Because at 0, what happens to our derivative? It's undefined, right? Hey, but that's a corner, so it should be undefined, right? So does that formula make sense? Okay, now let's see if you can extend that idea. Let's say I give you this absolute value of sine x and ask you for the derivative. So the derivative of this would be, you have to use chain rule still. What's the derivative of the absolute value of something? Well, what's the derivative of the absolute value of something? Either one of these. That's something over the absolute value of that something. So this should be equal to that something over the absolute value of that something, right? Times, here's the chain rule, the derivative of what's in here, which is cosine x. And no, these do not reduce out to be 1. It's not 1, because it depends on the value of sine. If this turns out to be a negative number, right, then this is going to turn into -1. If this turns out to be a positive number, it's going to turn into +1. Make sense? So let me show you the graph of absolute value of sine of x. Abs sine x. There's the graph of the absolute value of sine x. It's basically taken your sine function and it's taken all those portions of it that used to be below the x-axis and moved them up top, right? Now I want to graph for you its derivative. The derivative would be sine x over absolute value sine x. Okay, do y'all see that right there, it cannot possibly be the answer so far? Do y'all see right now all I've done is I've typed in this part, sine x over absolute value of sine x, and look at the derivative. Right? It's saying that this is the red one, right? This is the original curve. The slope of the tangent line right here is positive, right? And as you move here, it's still positive, but it's changed, hasn't it? This right now is just saying it's positive and it's the same value the whole time. I need to somehow tweak this to account for the curving. So that's where that chain rule part comes in. I was missing the cosine, right? So if I do times cosine x, there we go. So check this out. What's the slope of the tangent line on the red one here? Looks like it's positive about 1, right? Maybe? And then what happens as I move to the right? What happens to the derivative? Still positive, but what? Gets decreasing, right? And then I get to the top here, the derivative is 0. Now I'm going to have negative, negative, negative until I get to -1. And then what happens here? Complete chaos, and I'm back up to 1. And then it does the same thing again, then it splits again. You'll see that? Okay. So derivative of absolute value of something is, that's something over the absolute value of it, and then you have to do chain rule of anything that's inside. All right, I sent an email about the test being moved officially, right? It's going to be on Thursday. Look at that right there. Oh no, is that not it? Where is it? There it is right there. I could click on that right now, couldn't I? I could click on that right now. That's the exam from another semester. So what I'm going to do is I'm going to send you all another email here in the next few days where I'm going to kind of give you a list of topics to look at for the test. But just remember me, this test is going to go back to L'Hopital, right? L'Hopital's rules in here. What's that?
Was it not?
Related rates, right? So take the time this weekend to just, run through your homework. I'm not saying redo it because you've already done it all. So, just go through everything. Take some time to refresh yourself because some of those topics seem so long ago,
2 weeks.
And then we will go all the way up. The test will cover all the way up through today. It is not going to cover what we cover on Tuesday. All right? So Tuesday, that material will be connected to this, but you won't be tested on it. All right. Have a great weekend, I think, right? Yeah, weekend, Thursday.